Hello, everyone. Today's topic is continuous random variables and distributions. Before we talk about continuous random variables and distributions, let's review the discrete random variables and distributions. Say we have a random variable x. The random variable is a function defined on the sample space. It has real values. Okay. Usually we use this notation to denote, say, it's PMF. Assume X is discrete, then we have a PMF. The meaning of PMF is pretty clear. F of X is equal to the probability that the random variable X takes value little x. So that's what it means. And then we have the mean and so forth. The mean, I want to just talk about mean for the moment. Okay. X times f of x, sum for all x. Okay. I'll go back to this later on, I guess. So for continuous situations, for continuous random variable, we would call it PDF. Okay. So there's a continuous case. Now the meaning of little fx is not exactly probability of capital X equaling little x. Because in later on we will know that the probability of x taking a value little x is actually 0 if x is continuous, assuming x is continuous. Okay. When we say a function, a random variable is continuous if it takes values in an interval or some union of intervals. All right. So the meaning of this is actually not that clear for the moment. We define a PDF through the probability. So if if there exists such a function a little fx, which is greater than or equal to 0, non-negative function, such that for any B is a subset in R, okay, so B is a subset in R, something like interval, for example, x is greater than or equal to little a less than or equal to b. Okay, that could be so our b is actually a b. It's interval. Okay, so for any uh, subset of R, the probability that x in B, so the values of x are in the set B, or something like this, right? This probably is a bit more, it's clearer. But in general, if there exists a function little fx such that for any b, the probability x in B can be expressed by this integral. Okay, then this little f is called PDF. PDF. Okay. Uh, when we apply it, sometimes we have a capital B like the interval. Then you would have the probability of x greater than or equal to a less than or equal to b that equals the integral from a to b of fx dx. Okay, that's how we define a PDF. The word PDF means probability density function. Again, this is actually not equal to the probability of x equaling little x. In fact, if you look at this equation, if a equals b, so that's just the probability of x equaling a, right? And then you have an integral from a to a. fx dx. This is actually 0 according to the calculus result. Okay. Geometrically, what it means is that the probability of a particular event or in this interval, then it's just the area under the curve of this density function. For example, if we have a density function, let's say call it bell-shaped curve. This is sometimes, well, we will do this a lot later on. This is our A, this is our B, then this area, no, this is fx. This area is the probability. Area means the probability. This is the probability of x greater than or equal to a less than or equal to b. That equals the integral from a to b of little fx dx. When x is continuous, we don't really make I mean, if they have a strict inequality, and the probabilities will be still the same because the probability of x equaling a0, probability of x equaling b0, so they're equal. And of course, you can do that as well. They're all equal. This is the property when x is a continuous random variable. All right, so that's the concept of a PDF. All right, let's move on. Let's look at an example. Let's look at this example. Yeah, so this is our density function. Little fx that equals c times 4x minus x squared. And x should be x greater than 0, less than 2. So this is our density function. We need to find c. In order to find c, we need to use a fact about this, the answer to this question. The probability of x greater than negative infinity, less than positive infinity, that can be expressed by that. That is basically the probability of x taking all the possible values. It's like if we consider sample space as all real numbers, then it's basically the probability of x in the sample space according to one of the axioms of probability. The probability of the sample space is always 1, so this is 1. Okay, so we're going to use that fact to find c. So let's set up the equation. So the integral, originally we have this, okay? This is always true. 1 equals that. Now, when you plug in this function to this integral, you need to be very careful. This is not right. That is not correct. And that's not correct because the function given is defined not as non-zero from 0 to 2, but after outside 0 to 2 it's actually 0. That's assumed. But it's actually written here 0 otherwise. So you cannot put the lower limit and upper limit as negative infinity and positive infinity. You need to change it to from 0 to 2. Okay, that is correct. Now we just do the antiderivative. And let's pull out c. the antiderivative for x, which is 2x squared, and then you have minus 1/3 of x to the third. That's the antiderivative. And then evaluate from 0 to 2. So that equals c times, plug in 2, 8 minus 8 over 3. That's 16. C times 16 over 3. Okay. We know that is 1, so we find C to be 3 over 16. And let me put somewhere here. C equals 3 over 16. So this fx equals, let's put it this here, fx equals 3 over 16 times 4x minus x squared when x is greater than 0, less than 2. Okay, maybe those things, some space. All right, so next we want to find the probability that capital X greater than 1. According to the definition of a density function, you see this one is the integral from 1 to infinity. Let's put density function in general here. But again, once you plug in this density function, 3 over 16 times 4x minus x squared dx, you really need to change the upper limit from positive infinity to 2. Okay. Then we do the antiderivative again. That's 2x squared minus 1/3 x to the third from 1 to 2. 3 over 16. Let's do, you have 8 minus 8 over 3 minus, plugging 1, you have 2 minus 1/3. So that equals 6 minus 7 over 3. Okay. All right. So that equals 11 over 16. Okay. Let's double check. Let's do it to find the integral from 0 to 1. That's actually a little bit easier to calculate. Or less than equal to 1, less 1 in terms of the probability. They are the same here. From 0 to 1, 316 times 4x minus x squared dx. Antiderivative, 2x squared minus 1/3 x to the third. Now x from 0 to 1, it's a little bit easier. And what is that? So it's 2 minus 1/3, which is 5 over 3. And you then you need to multiply by 316. 316, so it's 5 over 16 actually. 5 over 16. And you add these two, you would get 1. So I think we were right. We didn't make any mistake. And you actually could find this probability by 1 minus this because I think in terms of integral, this is easier to calculate. All right, so that's one and two. Okay, capital Fx. So let's introduce the CDF. So CDF is the cumulative distribution function. There's a definition. What is a definition? Definition is a cumulative distribution function. It's the integral of the density function from negative infinity to little x. Oh, this is actually little x. All right. Okay, so one mistake I see a lot is that when they're gonna change this to positive infinity, but that's actually it's not a function anymore. It would be one. So it's a function with respect to x. The upper limit of the integral is x. So for this example, we have 316, right? C is 316. So capital F of x equals, by definition, okay. Oh, by the way, I think we probably should change this x to something else. Uh, so otherwise it would be a little bit annoying. I mean, you have this x here, you have another x here. It's a little bit confusing. If we, let's change it to t. So I have ft dt. So this ft is very general, so it's always true. This is the definition. So, but once you change to the given little ft, times 4x minus 2x squared dx. Um, okay, I'm trying to recall the value. The lower limit is 0 and upper limit is x. We should change to t. Okay, so antiderivative to t squared minus, 1 second. I have something, I don't feel, did I make a mistake here? Uh, Sorry, let me check it. Did I forget 2 times x squared somewhere? Uh, yeah, I think I forgot. All right, so I think okay, we're gonna just change the. I don't want it to change what I did. So let's uh, assume the original function is 4x minus x squared. Okay, I have a c equals 3 over 16. So I remember that. Okay, so forget about that. All right. All right. So fx from negative infinity to little x, put the fx here. And once we plug in the function 3 over 16 times 4x minus x squared, uh, put t here, t, and dt from 0 to x. And then I have a antiderivative of 2t squared minus 1/3 t to the third, and t from 0 to x. So I have a 3 over 16 times 2x squared minus 1/3 x to the third. All right, so this is our CDF. I do need to specify this is when x greater than equal to 0, greater than equal to the actually doesn't really matter much. Doesn't matter. I have that. Uh, if you are asked to give CDF fx on the whole real number line, then you actually need to specify. So something like this, you need to specify that's piecewise defined function. It's 0 when x is less than equal to 0, and it is 3 over 16 times 2x squared minus 1/3 x to the third when x is greater than 0 and less than 2, and 1 when x is greater than equal to 2. Okay, if you plug in 2, actually you do get 1. So do not assume that fx is this function no matter what, no matter what the value x is. That's actually not correct. Okay, so the complete answer for the CDF of or fx, capital Fx, should be written as something like this, the piecewise defined function. Okay. All right, let's study the relation between the PDF and the CDF. Obviously, CDF is given by the integral. Okay, so capital Fx equals the integral. It's the integral from negative infinity to x f of t dt. So this is one direction. You have a PDF, and you can you integrate to get capital Fx, which is CDF. Now, if you know CDF, how can you get PDF? So we know the fundamental theorem of calculus. Okay, the derivative of this quantity is simply little f of x. Okay, that's the fundamental theorem of calculus. One version. Okay, there are two versions. There's one of the versions. So we get this property. If you differentiate the CDF, you will get a PDF. All right, so this is the relation between these two functions. You need to be very familiar with them. Here's another example. I think it's probably easier. Little f equals cx, and x from 0 to 1, and 0 otherwise. Find c and then probability and capital Fx. Okay, so using the fact that integral from 0 to 1 c times x dx, that's 1, and we're gonna just find the integral, right? C times half x squared, x from 0 to 1, and plugging 0 you get 0, plugging 1 you get half c, so half c. So I get c equals 2. Okay, so c equals 2. And then we have this probability of x less than 0, 0.5. So we have the integral from 0 to 0.5. And you plug in cx, which is 2x dx. And then you have the antiderivative, which is x squared from 0 to half, right? So that's 1/4. So the answer is 1/4. Uh, capital Fx equals, oh, let's say, assume x is from 0 to 1. So I have from 0 to x, c times t dt. C is high is 2, so 2t. So that is just t squared from 0 to x. You get x squared. So capital Fx is 0 when x is less than equal to 0, and x squared when x is greater than 0, less than 1, and 1 when x greater than or equal to 1. So that's capital Fx. That's about the random variables and the continuous random variables and distributions. Next, let's talk about the parameters. Expectation. So for discrete distribution, we have expectation, which is the sum. Okay. For continuous case, you cannot have you cannot have a summation anymore. Summation is works for uh, kind of countable set. If you have uncountable set, you really cannot use summation. Instead, we have a integral. Remember, integral, this notation really comes from S, which is the summation, the first letter of a summation. All right, so in the uh, continuous case, E of x, expectation of x, is defined to be the integral from negative infinity to infinity, x times fx dx. So that's the definition of expectation. All right. So let's have a look at this example. That c, so little fx equals c times e to the negative 2x when x is greater than 0 and 0 otherwise. Again, we need to find c. So let's do that from 0 to infinity, c times e to the negative 2x dx. That should be 1. Okay, the integral from negative infinity to infinity of the density function is always 1. But here, the density function equals this exponential function when x greater than 0, but 0 otherwise. That's why you need to change the lower limit from negative infinity to 0. Okay. So the antiderivative of e to the negative 2x is negative 1 half e to the negative 2x. Okay. You can differentiate it, and you can see very quickly that the derivative is e to the negative 2x. From 0 to infinity, when you plug in 0, obviously you get oh, you plug in infinity first. You plug in infinity, you have a negative 2 times infinity. So it's basically the limit of e to the negative x when x goes to infinity. That's 0. So you have 0 minus. You plug in 1, you plug in 0, so you have c times negative half. E to the 0 is 1, so that's just that. So I have a positive half times c. That equals 1, so I can claim c to be 2. Okay. Later on, you will know this is the exponential distribution. So anyway, I have the c equals 2. Okay. Let's find mu. Mu is the expectation. Okay. E of x equals mu. In general, okay, by definition, so let me write the definition down. Uh, I just want you to be aware. Okay, I emphasized a few times already. Once you plug in the given density function, you have to change the upper limit or lower limit if necessary. Here, you need to change the lower limit. The upper limit, you don't. Okay. What is x is and some x somewhere. X times that. Okay. All right. For this type of problem, you need integration by parts. All right. So integration by parts. Uh, there are different ways of writing the integration by parts. Uh, the one I like is usually something like UdV, and then you have a UV minus integral of VDU. So this is the version I like. But then you can also do something like U times V prime dx, or U both UV are functions of x. So that equals UV minus the U prime V dx. They're the same. This is differential, this is the derivative. Uh, I feel like this is probably easier for me, but some people like you using this version. That's totally fine. But because I like this first version, I'm gonna use this version most of the times. So I know that this together, that is d of e to the negative 2x. Okay, so I have the integral from 0 to infinity x times d e to the negative 2x, and then use the uh, integration by parts, so x times e to the negative 2x minus, and then you just switch, right? You have a e to the negative 2x dx. I think I made a mistake somewhere. Sorry. I should have a negative sign here. You differentiate, you would get positive 2 times e to the negative 2x. So I need to put negative sign here. And then you subtract and you have a negative sign here. So basically, you're gonna just switch, okay? Remember the version I wrote, UV minus VDU, to basically just switch here, okay? All right. Uh, um, this notation might be confusing, but what I mean is that this one's basically just switch the order of these two things. Oh, I also forgot something else. G. Okay, so this should be x from 0 to infinity minus integral from 0 to infinity e to the negative 2x dx. All right. The first term, when x goes to infinity, you have infinity and then you have zero, so it's infinity times zero type. It's actually indeterminate. You need to, I mean, it's the indeterminate type. All right. It's actually the root, it has a value. It's determined, but the type is indeterminate type. It's infinity times zero type. You can use L'Hopital's rule. You do x over negative e to the negative 2x. It's positive 2x because it's on the bottom now. And you let x go to infinity, you take a derivative and so forth. That's fine, but just wanted to give you a very simple fact. Exponential function goes to infinity or goes to zero much faster than polynomials. So x goes to infinity, no problem. But this then goes to zero faster, e to the negative 2x when x goes to infinity. So this e to the negative 2x goes to zero. It's a fact. Okay, you can use L'Hopital's rule to prove. So this thing goes to zero. This thing goes to zero faster than x going to infinity. So when x goes to infinity, this whole quantity is zero. And when x equals zero, you plug in zero, you do get zero again. So this quantity will just disappear. Yeah, the whole quantity will disappear. And then we left this quantity, e to the negative 2x dx. This is good. You cannot have negative sign here or negative sign outside. Both is okay if it cancels out, but you cannot leave something like this because this is a positive function. Um, so this is good. At least it's a probability, so it has to be non-negative. So This is one way of checking when if you're making a mistake or not. Anyway, let's continue. The antiderivative is negative 1/2 times e to the negative 2x. And then from 0 to infinity. You plug in infinity, you get 0, minus negative half. Plug in 0, you get 1. So it's just half. So the expectation is half. Okay. Later on, once you learn the exponential distribution, and it's very easy to know, it's simply 1 over this quantity. You have say lambda times e to the negative lambda x. It's the density function of exponential distribution, and the mean is just 1 over lambda. Okay, uh, we'll talk about that later on as well. Okay, so that's mean. All right, so sometimes we wanted to find the expectation of a random, so function of a random variable. So capital X is a random variable. G of X is a function of a random variable. Uh, we can claim that this quantity uh, can be found by using this integral, little g of x times little f of x dx. This is the density function of capital X. Okay, so again, we have a sort of this assumption at the very beginning, PDF. Okay. All right, so this is the way of calculating the expectation of function of a random variable, especially when we have e of x squared. We need to use this a lot for variance. So that's just the integral from negative infinity to infinity. And the integrand is x squared fx dx. So that's this quantity. The expectation of a linear combination of two random variables is still the linear combination of the two expectations. We talked about that expectation is linear for discrete case, and it's also true for the continuous case. So this is always true. All right. Here's an example to find expectation of e to the x when the density of x is given. So what it says is that we have a random variable, PDF, which is 1, f of x equals 1, when x greater than 0, less than 1. This is a type of a uniform distribution. Okay, it's the PDF is constant. So how to find that? Expectation. Okay, remember this is actually a random variable. So this expectation of e to the capital X. So this is random variable. So it's defined to be the integral from negative infinity to infinity, little x, not little e to the x, actually not little x anymore. So it's a function of x. So e to the x times f of x dx. Okay, this definition is not wrong, but once you plug in this density to this to the integral, you actually need to be very careful. I emphasized many times already. X should be from 0 to 1, then fx equals 1 dx. Okay, don't write it something like this. Okay, that's very wrong. Actually, it's a diverge. It's a divergent integral, so you cannot do that. All right, and that equals the antiderivative of e to the x, and then from 0 to 1, e minus 1. That's the expectation of e to the capital X. Okay, so next concept, expectation, then variance, right? The next concept is variance. Variance of a random variable, the definition is actually the same as the, the case when x is discrete. This one is the same. And also we know uh, this formula still works. Okay, so that's the definition of variance. But in continuous case, we don't have the summation. In this case, we have summation. Okay, that's a sum or something like that. But in a continuous case, you don't have a summation. Instead, you have an integral. So for the first, this one is the integral from negative infinity to infinity. X minus mu, you change to little x, squared, fx dx. All right, so this is this one. And here you just find the second moment and then find this first moment, and you get variance. All right. And standard deviation is defined to be the square root of the variance. It's the same. Yx is discrete, so they are, in terms of definition, they are the same. All right, so we have this examples, fx equals 2 times e to the negative 2x when x greater than 0. Okay. Let's try to find the variance. I'm going to use e of x squared, then minus e of x, then squared. So let's do e of x squared, which is the integral from negative infinity to infinity, x squared fx. And then once you plug in this function, you have a 2 times e to the negative 2x, and you have x squared here. And then you need to change the lower limit to 0, keep the upper limit. Let's do this. You have a x squared times d of negative e to the negative 2x. Okay. And then integration by parts. 0 to infinity, x from 0 to infinity, and then minus, a little bit annoying, so I'm going to erase that. You have x from 0 to infinity minus switch. You have a negative e to the negative 2x dx squared. Dx squared is 2 times x dx. All right. And again, when x goes to infinity, this thing goes to 0 faster than x squared going to infinity. So this dominates and it becomes 0. And when x equals 0, you plug in, obviously, it's 0 times 1 is 0. So this term disappears, and you have a 0 to infinity. Negative negative cancels out. You have 2 times x times e to the negative 2x dx. Okay. Let me adjust the order a little bit. So you have x times 2 times e to the negative 2x dx. What is this quantity? This is actually the expectation of x, and we just calculate that one is actually 1 over 2. Okay. This type of application is very useful. For exponential, the exponential distribution. The mean of the exponential distribution is 1 over lambda. So that's just very useful later on. It will save a lot of time. Otherwise, you need to go through the integration by parts again. Okay, we don't want to do that. All right, so that's our second moment. So the variance is the second moment minus the first moment squared. Second moment is 1/2 minus the first moment squared, which is 1 over 4. So it's 1 over 4. Okay. All right. Okay, so we have the variance, and the standard deviation is simply the square root of that. Sigma equals 1/2. All right, I think, is there any more example? I think that's it. Yes. Next class, we're going to talk about some continuous models, uniform random variables, and then we have exponential random variables and normal distribution. Okay, these things. That's for today, and I'll see you the next time. Bye bye.